kind of like okay, good.
But
it would have been much better if we were able to schedule the one place from beginning, rather than I had to say everything on the same place. I myself, I was going to the wrong place, and then I checked and I realized it was here. Yeah, that one, yeah.
Recording in progress.
yeah, just you need to just join the Zoom.
Yeah. Hello.
Okay.
Or you need clicker.
Yeah, is there a clicker? Just, I mean to point.
Yeah.
Yeah.
You need to.
Okay.
Maybe not very clear.
Maybe.
I think no.
Okay, but I can point with this. Okay. Should we close this? Also nee, das ist, weil es keine Slides sind, das kann ich nicht anders machen. Das ist so ein
So, ist
Notebook.
genau, das sagst du.
Ja, genau. Ja, mal gespannt, ich habe das zum ersten Mal mit so einem Notebook.
Das ist eine sehr gute Idee.
Ja.
Das ist aber alles mitmachen.
Ja. Vielleicht. Achso, da gibt es Background. Ah, okay. Was zum Halbieren? Oh. Ja,
You
hier.
can choose the color.
And how do you erase? Okay. Oh, okay, very good. Yeah.
All right, so good morning, everyone, and welcome to the third lecture in this mini course. And today I'm very happy to introduce Paul Hager from the Humboldt University in Berlin. And he will continue and show us some more practical aspects of calculating with signatures, particularly also in the context of the optimal stopping problem that we talked about yesterday. Please, Paul.
Yeah, thank you, Christian, and thank you for letting me give this lecture here and for all the attendants of this course, for their attention. So, as Christian said, I will sort of continue with his talk, just to give a quick outline. So I will concentrate actually on sort of the implementation of this signature stopping rules. So therefore, I will first go into how to calculate the truncated log signature for piecewise linear paths. Okay, we are on a computer, we need to discretize our time period in some sense. So this will be a bigger part of this lecture. Then the second part will be about the implementation of the signature stopping rule. So how we use deep neural networks to employ the log signature for the stopping problem. This is sort of maybe this is focuses mostly on the implementation. So this is I will show some code here, and then finally we look at the specific example of approximating the optimal stopping value of a fractional Brownian motion. So some of you have seen this exercise sheet that was distributed. We will use this code for the simulation of the fractional Brownian motion, and we apply what we do in the first step. We will calculate the log signatures, and then we will use this deep signature stopping rules, and finally come up with some approximate values for this optimal stopping problem. So before continuing with these slides, I will go back to Christian's slide actually, because there were a few slides left, which sort of give the introduction also to what I will do today. So this was one of the last things that Christian presented yesterday. So this is the linearization approach to optimal stopping using signatures, if you want. So especially the last result is that you can, undertaking some truncation and then taking limits for this truncation to go to infinity, calculate the optimal stopping value as a linear functional on the expected signature. Right? And then this is the shuffle exponential. So we have an infinite series here on the left-hand side. That's why we need to truncate the expected signature on the right-hand side. And then if we take this truncation to infinity, we actually obtain the true value of the optimal stopping problem. So numerically, we also implemented this and we tried this, but there are problems numerically, because obviously this truncation breaks the algebraic structure, right? So if you truncate, you will introduce an error because you're not respecting the true shuffle relation anymore, because higher order terms of the signature are eliminated. And therefore you do an algebraic error, and this algebraic error you can only compensate by using a very high truncation level, which, as Christian also mentioned yesterday, consumes a lot of memory, right? Because this signature, essentially the components of the signature grow in the number of d to the power n, more or less, and therefore this gets very quickly infeasible. And for the examples that we tried, we were not able to really calculate reasonable approximations with this approach. So there are two questions. I already sort of gave the answer. So this is due to algebraic errors. So, but the question could also be, could it also be that just the truncated signature doesn't contain enough information to do the optimal stopping problem, right? So in order to see if this is not the case, we wanted to see, okay, we use lower truncation levels and use nonlinear functionals, right? So because the only reason why we need to use high truncation levels here is sort of to compensate this algebraic error, but the signature maybe to level 3 or so contains already enough information that could be, and therefore we came up with another approach. So this another approach starts with the log signature. So this slide also Christian presented yesterday. It's just an example of this linearization. So the log signature is also Christian already defined this yesterday, is the tensor logarithm of the signature, which then gives an element in this free Lie algebra, or if you truncate in this free nilpotent Lie algebra. So the log signature contains the same amount of information. It just removes this or saves this algebraic relations in a more efficient way. Let's say it removes this redundancy in the signature that allow, on the other hand, to use this shuffle relation. Right? Therefore, one can see, okay, the log signature can be saved much more efficiently. This is something I will go into much more detail later. So here are some examples. If you are in dimension 3 and you truncate to level 6, the log signature has 196 components, while the signature has more than 1,000 components. So as I already mentioned, this is due to the fact that when you save the signature, you want to have these algebraic relations in a form that you can easily apply the shuffle rule. Right? So you have to save it in this tensor algebra, which consumes a lot of space, but it has the advantage that if you want to take linear components of the signature and then take shuffles of linear components and calculate in that way polynomials, it's very fast because the algebraic structure is already in place. If you go to the log signature, you remove all of these redundancies, you get a more efficient representation. But if you want to calculate a linear component of the signature, you have to reverse this compression again if you want. So this is a trade-off between, do I want the algebraic structure of the signature, or do I just want the information contained in the signature? And if I'm only interested in the information, I will use the log signature because I can save it much more efficiently. So this is about the log signature. How can we use this now for the optimal stopping problem? So as I said before, we want to replace now the linear functions by nonlinear functions that we can somehow optimize in some way. So I guess the most popular choice nowadays is anyway deep neural networks. So we start with the deep neural networks. I guess everybody is familiar with this definition. Maybe just, so this is a composition of affine functions with nonlinear activation functions. The first layer takes as an input the log signature. So the dimension k here will be the dimension of the log signature. Then we have a number of I-1 hidden layers with q neurons. And then the last layer will map to some real value, which will be our stopping rule. So this value will tell us then in the end how much we want to stop the process. So applying this for the signature stop, so for the stopping problem and defining a stopping time, we use the same approach that we used also for the linear functionals. So if we evaluate the log signature as time evolves with this neural network, then we get this real quantity, which is positive because we squared. And then we integrate this. So this integral will be, of course, an increasing function over time. And once this increasing function hits above this random threshold set, we will stop. So this was the same sort of parameterization of the stopping rule as for the linear stopping rules, only now that we replace the linear function here with a neural network of the log signature. And then we can also show that the same approximation result holds. So we can also show that the optimal stopping value is approximated by only using this type of stopping times. Right, and the proof essentially based on the proof of the other approximation theorem that we have for linear stopping rules and the universal approximation theorem for neural networks. So this is where I will go back to my other slides. So we are going to see how to use this on a specific example and implement all of the stopping rules. So therefore, let's quickly review the definition of the signature. Christian already did this yesterday. So we have a smooth path on some time interval 0 to t mapping to d-dimensional space. Okay, also notation. This d-dimensional space has a basis I1 to ID, which just for highlighting purposes, I will paint in blue. And then we have that the signature is the sequence of iterated integral. So the path integrated by itself over and over again in this tensor algebra. So in other words, this means the components of this tensor series are iterated integrals, one-dimensional iterated integrals. So if I take a multi-index, or we also call this a word in the letters 1 to D, and I take the corresponding component of the signature, I get an iterated integral of one-dimensional paths with the components corresponding to this word that I choose. And this sequence of iterated integrals is my signature. So this satisfies two relations, which Christian also presented yesterday. The first one is the Gen relation, which essentially is due to the linearity of the integral. So if I calculate a signature on an interval from S to T, I can subdivide the interval into two parts from S to U, U to T, and then I can just multiply these two signatures in the tensor algebra, and I will get the same object. The second one is the shuffle identity, which also was discussed yesterday. So it says that if I take two linear components of the signature and take the product, or more general, also a polynomial, of course, then I can calculate this product again as a linear combination of signature components. But of course, the shuffle product will produce a longer word, so I can represent this product of, let's say, lower order signature components in terms of a linear combination of higher order signature components. So this is exactly this algebraic structure that you want if you save the signature in this tensor algebra, what I mentioned earlier. So the elements in the tensor algebra that satisfy this rule, they form a group, which is the free Lie group. And taking the logarithm of that group, we obtain the so-called Lie algebra. And this is one way to characterize the Lie algebra. And the Lie algebra is, of course, the space where our log signature lives in, right? So we really want to understand this algebra a little bit better in order to calculate the log signature. So here is another way to characterize the free Lie algebra. So first of all, there's this commutator bracket. The commutator bracket on the tensor algebra first is just, okay, the usual commutator. We have a non-commutative product, so this is not zero, right? So, and this defines the commutator, and it satisfies these two relations. The first one is obvious. This is the antisymmetry. And the second one is known as the Jacobi identity, which is maybe not that obvious, but doing the calculation, this one will see that it's true with the definition of the commutator bracket. And this is sort of the two properties that any Lie bracket should satisfy. So this commutator bracket is a Lie bracket. The free Lie algebra can be characterized as the smallest subalgebra of the tensor algebra, containing the entire RD space. So the first order, the first degree space is contained in the free Lie algebra. And then everything that you obtain with taking brackets is also contained in the free Lie algebra. So in other words, as I wrote here, you can generate this by taking these basis elements and then taking iterated and all sorts of Lie brackets, and this will give you the free Lie algebra. Okay, what does this this characterization means for the signature. It means that the signature is an element in the Lie group, which we already knew. So the logarithm of the signature is in the Lie algebra. And as I just said, elements in the Lie algebra can be represented as in terms of brackets, right? So that means we have the log signature is of this form as some coefficients in terms of tensors, but these tensors are always in the form of brackets, right? So this is one observation. This raises two questions now, thinking about calculating the log signature. So the first one is, what kind of basis can we choose in the free Lie algebra? So I showed before the algebraic properties of these brackets. So there are a lot of redundancy if I take all the brackets. So I need to understand which are the least amount of brackets that I can use. In other words, which basis can I use for this free Lie algebra? And then once I have this basis, how can I calculate the coefficients in this basis, right? So we will first start with this. And therefore, we will first look at an example. So we have a two-dimensional case. We only have two indices, 1 and 2. And I also will identify now the basis element just with the index, of just with the letter of this basis element. And we can look at the terms that we obtain when taking brackets. So the first ones are, of course, trivially, the single letters are contained. So now I can take brackets of single letters. So what possibilities do I have? I can take 1 and 1, of course, and then I can take, I'm being very naive here, of course, you already see that some of the things that I write down here are 0. But these are all the possibilities that I have to bracket two elements, right? And already from the definition of the commutator bracket, it follows that this is 0, right? Because in the commutator bracket, if I take here these two products of 1 and 1 minus 1 and 1 is of course 0. And the same thing happens for the 2 and 2 element. This is also 0. And those are related by antisymmetry, right? So I know that this one is equal to minus this one, which is the same as this one. So I can remove one of them for my basis. And then we will see later a more systematic way to remove them, but I can remove this one. So these ones are 0. And what's left in my basis is just the 1, 2 element. So this is already, we have characterized now 3 basis elements. We have the 1, 2, and we have the, so 1, 2 as single letters and 1, 2 as a bracket. So if we continue, I can. What brackets we can obtain in the third order? We can take basis elements of the first order and basis elements of the second order and take brackets of them. I have 1 in the bracket 1, 2. Okay, now I can of course take also 1, 2 bracket 1, so replace them, but they will give me a linear dependent element, so I don't take this one. And then I have 2 and 1, 2. And more I can't do. So these are the only 2 elements we can obtain, and there are also no further simplifications. And so this will give us the 3rd degree basis. Are these 2 elements? So let's also do one more level. In level 4, what can we do? We can take one of level 1 and one of level 3. So this will give us this relation. I can take one, and then the first basis element of the 3rd level. You can also switch this again, but it will not give me a new element. Then I can take here the 2, of course. Sorry, I have here also, let's go ahead here. So we have here the 1, the first basis element of the first level, and also take the 2 here. Here's 2, bracket 1, bracket 1, 2. And here the same, so this is all the same. I didn't mean this one. Second basis element of the third order, right? It should, just to be probably more consistent, I should take here 1, and then the second basis element of the third order, and then of course also this one. These are 4 elements, and what I can also in principle do, which we will see of course is 0, but I can take 2 elements of the second level and also take the bracket. Okay, this one is of course 0 because there was only 1 element in the second basis, so we immediately see that this is 0. Now we have 4 left for the basis. But there are further algebraic relations in the spaces. We can see this if we take the one that I just erased. And then we apply our Jacobi identity. So let's say this is A in the above identity, then this is B, this is C. If I write that down, Jacobi identity will give me A, B, C. I bring the other 2 terms to the right hand side, so I will have a minus B, C, A. So B, C, A, and a CAB minus B, A, and your bracket with the B is 1. Okay, so this were again here all the possible. Okay, I can also write down the relation here that I just wrote down. So these were all the possible brackets, and now we see using the Jacobi identity, I get this 2. And then just by flipping one bracket here, so if I flip this over here and have to change the sign 1 time, I will obtain 2 elements that are already contained up here, right? So I will obtain this element and this element. So there's one more linear dependence, because if I subtract these 2 elements, they are 0, so they are linearly dependent. So I can also throw away one of them, and I will obtain for the base, let's say, these 2 elements and this one. So I have 3 basis elements in the level 4. So let's summarize these elements that we had for these ones. And counting them means, okay, we have found 8 elements up to level 4. That means the dimension of the nilpotent free Lie algebra of level 4 in dimensions 2 is 8. Right? And if you compare this to the dimension that you have for the truncated tensor algebra, you already see that it's much more efficient, because the dimension of the truncated tensor algebra of level 4 in dimension 2 is 30. And so we compare 8 to 30. Now the question is, can we do these calculations that we have done here by hand in a more organized way to find a general basis for a general approach to calculate a basis of the Lie algebra? And the answer is, of course, yes. And one way to do this, there are different ways, and one way to do is called is through words that are called Lin words. Unfortunately, I won't have the time to go to in all the generality, but we can look again at the example. So for this example of d equals 2 and up to level 4, these are the first Lin words, right? These are all the Lin words up to level 4. Okay, why are these the Lin words? I didn't give you the definition. The definition is that each of these words comes before all the proper suffixes in lexicographical order. So what does this mean? Let's look for 1, 2. This is trivial because they don't have suffixes, proper suffixes. Here, the word 1, 2 has one proper suffix, so a proper suffix is one that is not the entire word itself. Right? So 2 here is a suffix of the word 1, 2, but it's not the entire word itself, and it's clearly in lexicographical order larger than 1, 2. Right? So this is a Lin word because it satisfies this. And then here we have the next word in this Lin words. So we have that the word 1, 1, 2 has 2 suffixes, 2 proper suffixes, 1, 2, and 2. And they are both also larger than the word itself, and the same here for 1, 2, 2. Also satisfied, and so on for 1, 1, 2. We have 3 suffixes. They're all larger and so forth. So this is the property of the Lin words. And how can we go from Lin words to the basis? So first of all, there's one more property. Each Lin word has at least one proper suffix if it has more than one letter, of course. And among these suffixes, there is also one, at least one, it is a Lin word, and then we can identify always the largest suffix of the word that is also a Lin word. Here we have the word 1, 2, and it has just one suffix, and this is a Lin word because it's just one letter. We have the word 1, 1, 2, which has 2 suffixes, but also the larger one, the 1, 2, is also a Lin word. So this is the maximum length Lin word. And then here, this is maybe a more interesting example. We have 2 suffixes, but the longer one, the word 2, 2 is not a Lin word, right? Because 2, the word 2 is in lexicographical order smaller than the word 2, 2. And so on. So we have here then more Lin words, and it's always the maximum suffix Lin word. So we can use this to map to the tensor algebra in the following way. So first of all, we take letters to primitive elements in the Lie algebra, and then we define recursively. So I didn't mention this in detail. So sigma is supposed to be a map from all the Lin words into the Lie algebra, right? So we want to have a bracket expression as the map of sigma. And then we decompose this word W into V and the largest Lin word suffix. And then we apply this map sigma to the one component and sigma to the other component and take the brackets of these two in this order, right? So let's look again at examples, or one example here. So we have this word 1, 1, 2, 1. The largest Lin suffix is 1, 2, 2. So I take the bracket of 1 and whatever I get from this 1, 1, 2. And then recursively, I have here the largest Lin suffix is just the letter 2. So I apply sigma to the first one and sigma to the second one, but sigma of 2 is just 2 itself. And then finally, I get this bracketing expression. This is a systematic way. And what I can't prove here, but it is true, that if I map all the Lin words with this map sigma, I will obtain a basis in the free Lie algebra. Right? Now, if you wonder how can we calculate the dimension of the Lie algebra, we have to count essentially these Lin words. And algebraically, this is related to necklaces. It's a algebraically involved computation, of course, but one can show that this explicit formula holds for the dimension of the free Lie algebra. This is a sum over divisors, k divides n, and then we have here the Möbius function, a special function in algebra. And we can, of course, calculate this for some values and compare. So here we compare the dimension of the freely algebra with the dimension of the tensor algebra, the truncated tensor algebra. Right? I already gave some examples before, but here are more examples. So in general, one sees, of course, that the freely algebra is much more low dimensional than the tensor algebra. There any questions maybe so far? We move on now to our signatures again. This was an excursion on the freely algebra. And we will look at signatures of piecewise linear paths. So we will, in other words, start with a discrete time series of data points, x0 to xj, d-dimensional. And we will linearly interpolate this path to obtain a smooth path, and then we can calculate the log signature of this smooth path. Okay, we will also define here these increments by delta xj. So first of all, note that on an interval from j minus 1 to j, on which the path is just linear, the signature or the iterated integrals have a simple form. Okay, so this is always t times delta xj, so I can take this delta xj out, take the nth tensor product of this if I have n iterated integrals, and then I will just have to calculate the volume of the simplex that I'm integrating over in the time component, and this will give me exactly this element. Right, so the signature is then given by summing up all of these elements in the tensor algebra, and which is exactly the definition of the exponential in the tensor algebra. So the signature of a linear path is just the exponential of the increment of the path. Now we have Chen's identity, and if we apply the Chen's identity to our piecewise linear path, means that I can subdivide the interval in all these subintervals where the path is linear. I know the signature on these subintervals. And then if I want to obtain the signature on the entire interval, to just multiply these exponentials. And that's exactly the question. How do I multiply these exponentials in the tensor algebra? Right? This is not commutative, so I can't just take the exponential of x1 plus x2 and so on. Right? This is exactly the point of this non-commutative tensor algebra. So I need a way to express this. And of course, I want this to be expressed because I'm interested in the log signature. I want this to be expressed as an exponential of something, and that something is in the Lie algebra. So I want this to be calculated in my Lie basis in the end. Right? The theoretical result is called the Baker-Campbell-Hausdorff formula plus Dinkin's formula, because this is a special form of this formula, which is historically, I mean, Baker and Hausdorff, of course, they worked at the beginning of the last century on this algebraic relations. Dinkin was, of course, a little bit later. So it tells us that if I multiply two elements in this tensor algebra, two exponentials, and take the logarithm, I can express this in terms of brackets, right? So this is what we expected. We can calculate it in terms of brackets, and this is the precise algebraic relation here, where this power means taking the exponent times brackets with what comes afterwards, right? So this is an explicit expression, but there are problems because this expression is not in terms of a Lie basis. So if I would really put this into a computer and calculate all these brackets that come out, there would be still a lot of redundancies that are in this formula. So the question is, we have already discussed the Lie basis. Can I also calculate this Baker-Campbell-Hausdorff formula in the Lie basis directly? And the answer is yes. but also we can't discuss this in detail, unfortunately. So there are ways to algorithmically compute the BCH formula in terms of the Linden basis, which then in turn tells us how to calculate the log signature in this Linden basis, right? Because in order to calculate the log signature, we just have to multiply these exponentials and then take the logarithm. So just for the first orders, this looks as follows. So this, you don't even have to use the BCH formula if you are just interested in the first few terms. You can also just multiply the exponentials, then apply the definition of the logarithm and see what really comes out. I think also Christian did this actually yesterday up to the second level for this Levy area. And here is also up to the third level. And this is already in our basis, in this Linden basis form, right? So this is just a calculation that we obtain here by hand. So coming back to our signature and looking at this BCH formula and looking at the Chen relation that we wrote above, we can now look at the specific case of d equals to 2 and see what will happen to the truncated log signature up to level 3. So first of all, because we know the log signature is in this so the truncated log signature up to level 3 is in this truncated Lie algebra, and we have defined a basis for this Lie algebra. So we know this log signature up to level 3 is given by some coefficients, which are defined here as this L index T, and indexed by the corresponding basis elements. So these were the first 5 basis elements of the truncated or of the free Lie algebra. Okay, so we plug this into the BCH formula. So using also this Chen identity. So again, this was from Chen identity. We can calculate the log signature until time j by subdividing the interval from 0 to j minus 1 in the last interval. And the last interval, I know the signature is just the exponential. So I have to multiply the signature up to j minus 1 with the signature on the last interval. And if I want to take the log signature again, I have to take the logarithm. So now we apply this above formula. Yeah, let me show you some more. We just plug into this formula for A and B. So here's the formula. For A and B, we just plug into this Lj minus 1 and delta xj. And this will give us this formula. Now we are only interested up to level 3. So I see, okay, this is something of order 3. This is something of order 1. So this is all good. Now here I take a commutator bracket, and I will take also the third order components and take the brackets with this first order component. And then there would turn out 5. There would turn out components of order 4, but I'm only interested in the level 3. So I can disregard them. So I can simplify this formula just by taking here the log signature up to level 2, up to level 1, and so on, right? So now we compare the coefficients to actually, we know the basis, we just want to calculate these coefficients. So we look at each component in this Linden basis. So the first component of Lj here is just, of course, the projection of those two, because everything that comes behind will be of higher order. So the first two are rather simple. Now the second level, I project this term to the second level, and I see, okay, what will happen here is of order at least 3, or is of order 3 since I truncated here. So I only have to look at this expression, and I only have to look at the first component of the log signature, because only this will produce me something on level 2. Writing down the possible, so the linear, the components of the log signature and the components of the path, I will obtain this formula for the second level. Right, and so we can project all of these terms, and we get explicit formulas for the coefficients of the log signature in this Linden basis. And this then, of course, tells us iteratively how to compute the log signature. We start on the first interval, we have the log signature, and we move on to the second interval, and we use exactly this formula to calculate the log signature until the second interval, and so on. So here's a code for this. Okay, so it's a long term because it's very specific what we're computing here. We want only dimension 2 and only truncation levels between 1 and 3. Then here are the dimensions of the log signatures of the corresponding truncation level. So we have already calculated the basis before, so we know log signature of level 2 has dimension 3, log signature of level 3 has dimension 5. And we define our array for the log signature. The first component, as also seen by this formula, the first component of the log signature is just the path itself minus the initial value. This is the first component of the level 1 components of the signature. That's why in the last index of this array are the components of the signature. So up to level 2, my signature is just given by this path minus the initial value. Now in level 2, I will use the formula that is presented just above this code. And I will just say, okay, the level, so the log signature in the second index, which corresponds to this word, to this basis element 1, 2, is given exactly by this formula in terms of the signature on the previous interval. So this L is the signature on the log signature on the previous interval plus the increment of the path, right? This formula and so on. For the third level, we have 2 basis elements. So we have 2 indices here for the third level. And in the end, using this iteratively over all time intervals, we obtain our log signature of truncation level 4. So we can check this algorithm quickly if it does what we expect it should do. So here's a path, a linear path, right? So we have, this is our path with these data points, 0, 0, 1, 1, 2, 2, okay, and 3, 3. It's a linear path. And what is the signature of this linear path? The signature is just the exponential of this increment. So this is the exponential of basically 3. 1 plus 2, right? Or let's write it in base terms. Okay, so and if I take the logarithm, this will give me the log signature, which is just this element. Okay, so it only has first level contribution, no higher order contribution, and this should be reflected by our algorithm. So let's calculate this. B is not defined, so I should first mark this. Okay, so this command is just to make this sort of table-like plot. Yep. Oh. Ah, okay. Also, this is not my computer actually. Your computer. So maybe just I will continue here with these examples. So we will see that only the first level of the log signature has non-zero values and all higher order values have 0. This should be done by the algorithm. Let's remember that we have also a second example. The second example will be this path. Oh yeah, okay, thank you. Okay, so as mentioned, all higher order terms are 0. And in the end, we have here the 2 3s in the first 2 elements of the log signature. So the second path is this one. Actually, there was no data point here, so we have just here one, here one, here one, here one. So this is this path. Now we have to look at this path over time. So let's say until here. If I go the area that will be generated by the path. So the area, as also Christian mentioned yesterday, the area is the second order component of the log signature, right? This is the area that is sort of surrounded, enclosed by this path. Here is a straight line, is a linear path. It doesn't enclose the area. So if I go up to level 2, I will now enclose this area. And if I go up to level, up to time 3. Oh yeah, okay. That's what it is. Time 3, I will end up here, and I will enclose this area here. And these areas have a negative sign because they sort of lie below the path, right? So this one, so this is here, this point is 2, right? So this area is just 1. This area is actually 2. Then if I proceed here for the last one, I will obtain this. So I will obtain this area in the last one, in this area, which are the same volume-wise, but have a different sign. So in the end, I will expect that the area is 0, right? Because these 2 areas cancel out. So what I expect again for the area is 0, 1, 2, 0. Let's see if this is also reflected by the algorithm. I mean, of course, because I tested this, otherwise I would have made sure. But so the first components are, the first component here is sort of the time index, if you want. The second component here is the index of, so the index of the y-axis. And the third component is the area, and it does exactly what I just said. So it is 1, so sorry, -1 because it's below the path, then -2, and then it cancels out in the end, it's 0. Right, and the higher order components are a bit more tricky to interpret. Right? So there are some interpretation in terms of higher order volumes, but it's a little bit tricky. So let's finally say we did this now for this example of 2 dimensions. With this approach of calculating the BCH formula in the Linden basis, one can do this for higher dimensions and also for higher truncation levels. So there is a package called the II signature package, which implements this to calculate the log signature, and which I wrapped around the previous code. So I didn't want to throw away our previous code here. So I used for this dimension 2 and level up to 3 previous code. And then for the other cases, we do one step. So this II signature package pre-calculates basically the BCH formula in the Linden basis. It's something that you can also store on the computer if you want. So you can do it for a high truncation level and a high dimension, and once calculate the BCH formula in the spaces and then save it. And then using this pre-calculation, we calculate the log signature on each consecutive interval using this pre-calculated BCH formula. So the reason why I still use this code is because unfortunately this II signature package doesn't provide a function to calculate the log signature on each subinterval. So I can only calculate on the entire interval. And of course, if I do it in this way, as I did it here, I throw away computations, right? Because I can always use the signature, as we did in our algorithm, the log signature of the previous interval to calculate the next one. So if I do it in this way, this calculations are thrown away in some sense. Okay, so this was the part about calculating the log signature. Now we'll come to the second step, which is about implementing the deep signature stopping rules, which was on the first slides, for the log signature. So recall, first of all, the definition. I also presented this already today. We can define stopping times by taking these functionals of the path, which for us will be deep neural networks of the log signature, integrate this quantity, and then stop if we reach above a random threshold. So again, the setup is that X is some underlying path, a rough path possibly, which also generates the filtration. Then theta is some continuous functions, as I said, will be a deep neural network for us. And Z is some positive random variable, a threshold that is independent of everything else. And in these approximation theorems, so okay, also we studied linear functionals, now we look at deep neural networks. And in this approximation, so this comes here. So here's again the neural network setup. I also mentioned this earlier. So we take this neural network and apply it to the log signature and then plug it into our signature rule here. And this is the setup of the neural network. I already explained this. And then we have also this approximation theorem, which are also presented on. So in this approximation theorem, and also for the linear stopping rules, one of the essential steps was the randomization, and the expression of the optimal stopping value, or sort of just of the stopped payoff, if you want, of the stop value of y in this form, right? We can express the stop value, the expectation of the stop value of y without using the stopping time, but just using the stopping rule, right? And this is a smooth function of the stopping rule. Where here specifically we have chosen exponentially distributed random variable. One can also choose something else, but this is of course one of the more simple examples. Now this tells us, I mean, this was useful in the proof, but it also tells us how to calculate or how to approximate the optimal stopping problem using our deep signature stopping rules. So looking at this expression, here are thoughts on the numeric side. So we can simulate our path on a discrete time grid, of course. We can calculate the log signatures with the methods already presented, truncated up to some level n. We replace the expectation by a Monte Carlo sum. We replace these integrals by discrete sums over this time grid and have an approximated value for that. And then, since it's a smooth function of our signature stopping rule, which is a deep neural network, it's a smooth functions of the parameters in that network, and we can use stochastic gradient descent to then try to maximize, so gradient ascent to maximize this value. Now, once we have then approximated some stopping rule, we can resimulate, so we can simulate everything again, and then plug and calculate this approximated value of this expectation again, and this will give us a lower bound. So first of all, it's a lower bound because we are suboptimal in our stopping rule, right? We go a specific class of stopping times, which in the supremum, of course, obtains our true value of the optimal stopping problem, but we are only approximating this optimum. And discretizing the time grid will also just lower the value of the optimal stopping problem, right? Because you have fewer choices, but it's still a lower bound. So that also means that if we do computations and if we evaluate our computations, the larger the number we get, the better our algorithm performed, right? It's so simple to compare these approaches. So before the implementation, one remark, and this is also a question that was raised yesterday. So if you think about our neural network, so let me just mention this again here, our neural network. How does it look like? It's a neural network that has parameters. The last layer, or the first layer, if you want, gets input dimension of the log signature of truncation level n in dimension d. Okay, so and this network is fixed. Now, if I change the time grid, for approximating the log signature, I don't change any of these parameters. I don't change the truncation level. I keep the dimension the same. I can keep all the parameters of the neural networks the same and can make my time grid finer. So, because this is in contrast to this other method. I'll go back to where we stopped. There was this other method by Becker, Geredito, Jensen, where you lift your possibly non-Markovian path to a n times d dimensional path just by including always the entire path. And then you apply Markovian methods to solve the optimal stopping problem. But of course, if you use this approach and you make your time grid finer, you will increase the dimensions or the input dimension of your neural network. And therefore, you will increase the number of parameters of your neural network. And this may be okay for some values of the time grid, some discretization of the time grid. But at some point, this will become also infeasible. At some point, also the numbers of parameters are too much. I mean, just because learning will get very difficult. So, and this doesn't happen if we use a log signature. A log signature is independent. So the log signature up until some time is independent of how fine I discretize the time grid before. So here's an implementation of this this deep neural network approach. So the first code is just a deep neural network. So it's just a concatenation of affine functions and activation functions, where the activation function here that we choose the ReLU function. And then we have the number of layers, the number of nodes that we tell TensorFlow, so use TensorFlow Keras. The final layer has output dimension 1 because it gives us the signature stopping rule. Again, this flattening is just a technical aspect. So this one will just apply this neural network structure. This layer here, the integrated stopping rule, will do exactly what it says. So we'll take what comes out from this neural network. We will square that quantity and then iteratively or cumulatively integrate. Right? So this is this integrated stopping rule. The integral from 0 to t over theta squared in a discretized version, of course. And then finally, the last layer, yes, is the randomized stopping layer. So this essentially takes the rule, the integrated rule, applies the exponential of it, and integrates it with respect to y. So let me just. Oh, okay. So I'm sorry, I realized that I did a mistake here. I can correct this quickly. We need to. Oh, sorry, not here. Oh yeah, awesome. Thank you. Since I'm here, I can. So here, okay, no. So I integrate in the end over the increments of y, right? Because we want the optimal stopping value, and we integrate over dy. So we take the stopping rule, the integrated stopping rule that comes out, take the minus exponential of it, and then integrate over y. So this is what this last layer is supposed to do. Take the minus exponential, take the increments of y, and take again this integral plus the initial value of y. And we add this, what comes out of this is the loss function. So minus what comes out, because we usually minimize for these neural networks, will be the loss function. And this will be the approximation to the optimal stopping value. Okay, so this was the implementation. Now we come to the final concrete example, which is the stopping of fractional Brownian motion. So I included this already on the exercise sheet. So we have fractional Brownian motion for some first parameter, h. H defines sort of the regularity of the path. H meaning slow, meaning very irregular. H being close to 1 means more regular. For h equals to 1/2, we have the standard Brownian motion. And now we can, and also let me mention this, it's not a Markov process and it's not the same martingale if h is not equals to 1/2. So that's why it's used usually as a prototypical example for studying frameworks where there's no Markovian assumption and there's no same martingale assumption. So we can time augment this path, and this is a rough path. I mean, we don't even have to lift to the first order integrals. This is just because we have two components, and one component is very regular. This is the time. This is a smooth path, and the second one is irregular, can be very irregular, but still I can define cross integrals between t and xt as Young integrals. And I can define integrals of the fractional Brownian motion with itself just by taking powers of the increments, right? If I integrate a path, a one-dimensional path with itself, I just get the squared of the increment, right? And so on. This goes for higher order components. So this is just to say that this example fits into our framework, and we can also calculate the log signature of this path. We are interested in stopping the fractional Brownian motion itself. So our payoff is the path itself, or the second component of the time augmented path. And then we'll first need to generate samples of the fractional Brownian motion. So this was on this exercise sheet. There's a very efficient method to do that using circulant embeddings and the fast Fourier transform. So here's the code for simulating fractional Brownian motion. So it's actually quite short. If you do it that way, you simply, so this is the code for calculating this, so for simulating a stationary Gaussian process that satisfies this property that the circulant embedding is positive definite. Then you can simulate just by simulating a m dimension. So m always reflects the number of sample paths that we want to calculate. So we simulate m times the length of our time grid sample paths, take an inverse Fourier transform, multiply it sort of with these eigenvalues of this circular matrix, circulant matrix, and then take the Fourier transform. And this will be applied to the fractional Brownian motion case. So this is the autocorrelation function of the fractional Brownian motion increments. And we just plug it into our algorithm, and then this will result in the increments of the fractional Brownian motion. So we integrate them again discretely. We will sum them up, and then we do a time change, because we have here simulated on the unit grid. But due to the self-similarity of fractional Brownian motion, we can scale it, and then obtain samples on another time scale. So here's an example. There's 4 examples of fractional Brownian motion for Hurst parameters 0, 0.1, 0.5, 0.9, and 1.0. So 1.0 is a bit special case. So we'll see on a time grid with 100 points and from 0 to 1. Okay, as I mentioned, or as you probably also know, the fractional Brownian motion for small Hurst parameter is very irregular. So for h equals to 0.1, we obtain this path. 0.5, the orange path that is behind here somewhere, this is the standard Brownian motion. And now increasing h even further, h equals to 0.9, will make it more regular. So here you see a little bit of the green path. And 1.0, h equal to 1.0 is just a straight line. So this means the fractional Brownian motion for h equals to 1 is just a straight line where the slope of the line is a standard Gaussian random variable. So thinking about stopping problems is of course very easy to stop this red line, because I just have to see, does it increase or does it decrease? If it decreases, I stop immediately. If it's increasing, then I wait till the end. Okay, so now let's collect all the code together. This function here adds all these layers that I defined before on TensorFlow. So we will say the time discretization, the degree of the truncation of the log signature, the number of hidden layers, and the number of neurons. Yes? Yeah. As I said, because it's the most popular choice nowadays. So, I mean, you could, of course, use something else, yeah. But you can also use neural networks. So we give these parameters, then we can calculate the dimension of the log signature using this II signature package, which is this complicated formula with the Möbius transform that I said earlier. Then we have 2 input layers. One will be the log signature, one will be the payoff. The integrated stopping rule is given by this dense neural network. So this parameter Q is not the number of neurons itself, but we take the input dimension. So the signature comes in with some input dimension, say 3 for the second level. And then we add Q more layers. Let's say we add 2 more layers, 2 more neurons. Ah, okay. Let's say our log signature has dimension 3, and then we add, let's say, Q equals to 2 more neurons on the second layer. All of these connections till the end, where we'll have always the same number of neurons. And in the end, everything gets, okay, there's the signature stopping layer. And everything gets down to 1 neuron, and then we apply the signature stopping layer to it. So this will give us the integrated stopping rule. Then we will apply this signature stopping layer, or this randomized loss layer, as I called it, which gives us the approximation to the optimal stopping value. And then we make a TensorFlow model out of this. And we also make a model out of this rule, the signature rule itself, because maybe later we will see how this actually behaves on a sample path. Then here's the code for calculating the log signature of the fractional Brownian motion. So we just simulate the fractional Brownian motion at time grid, but we also calculate the log signature of the time augmented path. So the first component will be just time. Second component will be fractional Brownian motion. Here's also a simulation. Have to, of course, run all previous. Okay, somewhere I didn't run a cell, so full log signature here. Here's just a plot of the first components of the log signature. It's fractional Brownian motion. So blue is the fractional Brownian motion, and then we have here in orange the Levy area between time and fractional Brownian motion and higher order components. Okay, now we are training the neural network. For the example, we use 100,000 sample paths for training. Set time equals to 1. Also the time interval from 0 to 1. N equals to 100 discretization points of the time grid. Degree 3, truncation level 3 for the log signature, and Hurst parameter 0.1. And we build our network, we calculate the log signature. We also simulate again for validation samples of the log signature. We say, okay, we use AdaGrad for optimization or optimizing our neural network, compile it, and then we fit it with respect to that data and validate it with respect to the independent data. Do that, okay. TensorFlow. Why this usage? Yeah. This one. Yeah, okay, yeah. Thank you. So this should compile now, and it doesn't converges. This was okay. This was sort of a charade because I did this on purpose. So we see, okay, the loss doesn't converges here. The reason is because you always have to fine tune your hyperparameters. I just want to say this is a priori not at all clear what you can use here. We have to change the learning rates to a smaller value, and then we see that it will compile. So here, this will be the negative approximation to the optimal stopping value. Right, for the Hurst parameter 0.1 and the time discretization 100. And then our validation, in fact, is already an approximation to the, or is a lower bound to the optimal stopping value.
Just to clarify, we don't want to see 0 for the loss here.
Oh, yeah, okay, yes. Yeah, because we want to have this loss as negative as possible because it's our negative optimal stopping value, which we want to have as large as possible, of course. Yeah. Yep. No, 0 would mean that the optimal stopping value is 0. Yep. Yep. Yeah, this could mean, for example, stop at 0 because the path is 0.
So here you said that you are computing a lower bound. So is there also kind of duality gap that you, I mean, you can also use upper bound for based on signature tools also?
No, this doesn't exist yet. This
Okay.
is something we still think about, but at this time, no.
Mm-hmm.
I mean, you can use, of course, other methods to calculate the upper bound, but
Any understanding, I mean, what is the challenge there compared, I mean, to the usual kind of upper bounds that are derived in the usual setting?
Yeah, at the moment it's not at all clear how to approach the upper bound. So the duality method with signatures. So where can the signatures come into that, right? So it's usually done by this martingales, dual martingales, right? And it's not clear to us yet how to employ the signature for the dual method.
Okay, thank you.
I just want to follow up on Shihev's question. Today he was asking you about the possibility to exploit this linear structure, right? And
Yeah.
you said, okay, it's popular to use neural networks. That's what we did, why we did it.
Yeah, yeah.
But if it would be indeed possible to exploit that linear structure, wouldn't we be able to get away with just doing a regression, say? And if so, there wouldn't be any learning, no hyperparameters, no training, no nothing. I mean, super quick, and very likely because it is a linear structure, one may end up getting some duality bounds that, you know, this is so complicated with all the nonlinearities that you get entangled into it, right?
Mm.
So
The regression, but then the regression in terms of like a backwards induction, or
possibly, or I mean,
because the
exploiting this dependence, this linear dependence with respect to the signature. I don't know how to do it, right? But,
yeah.
but if it would be possible, and if
Yeah,
you would
that-
be able to generate samples and then do a loss function and then regression, pure regression,
Yeah,
this is a linear regression. Okay, so you have to deal with the Gramian, use some large deviation theory to get the inverse sampling inequality to see how many samples you need for the number of basis functions you have, choose an orthogonal basis there,
Mhm.
and then boom, no training.
Yeah, that's a good point. Yeah.
And if I may, I think I can answer also a little bit here. I can make a comment on your question, and that is, say you're using dynamic programming, and as you say, in principle, we want to approximate the value function as I say, linear function of the signature. Now, the tricky part in all these approaches that we see is that you have at some point a non-linearity that you need to linearize. So for instance, if you use a standard dynamic programming formulation for this problem, you would have to take the maximum between the expected value, between the conditional expectation of the value function one step later with the current payoff. So you have to linearize the maximum. This is like we had to linearize the exponential function in our approach that we showed you. And yeah, and the problem that tends to happen, even though we didn't try it out for the dynamic programming, is that if you linearize a highly nonlinear function, and by linearize I mean you have to approximate it by polynomials, right? Because polynomials are linear functions somehow. Then you tend to have to go very deep in the signature. And that becomes very expensive if you do it, you know, in a straightforward way. Maybe you can do something using kind of hierarchical structures, but the difficulty in all of this, as far as we see, I think, is you have to linearize highly nonlinear functions which are kind of imposed on you on the problem, be it the dynamic programming or be it a more direct approach like we do here, like a policy parameterization approach. Yes. Yes, absolutely.
Yeah,
but to be fair, I mean, we didn't try that either, but I mean, Paul will show you that a relatively low dimensional, low number of features is enough. So maybe something like a simple, a much more simpler regression algorithm could work here as well.
Mm-hmm. Mm-hmm. Yeah, thanks for the remarks. Huh?
Sorry for
No, if I still have, yeah. So this was the training. Now we can, as mentioned before, we can calculate lower bounds. those essentially also reflect lower bounds. And usually one if I would really want to calculate an honest lower bound, I would need to use some more samples here. This would take too much time. So we can resample our log signature and then predict with our model the approximated stopping value. And then also calculate the Monte Carlo error. For this 0.1, we have now 1.030. Of course, we can also optimize this a bit further by using more samples and more training. Already okay. So this is what I mentioned earlier. So we have also used this rule itself as a model. So we can evaluate the signature stopping rule along some sample paths. That's what we do here. So we have our fractional Brown in motion, and we have so on this axis, and this axis will be for the rule, and we have our random threshold set, which in this sample lies here, and then the signature rule, if it's high, will tell us okay, stop. If it reaches above the threshold, we will stop. And then it's probably for this example of this very irregular path a little bit hard to understand what motivates this problem, but at least it's not, maybe it's not a very trivial rule here. So in general, we see maybe that if the path spikes up highly, then we will increase our rule in some sense, because as Christian also mentioned yesterday already, the increments are negatively correlated. So a high jump upwards is correlated or will lead likely to a low jump downwards. We see this again, and then maybe here's a spike, and then here in this one, where it spikes up here, this is where the signature rule really says, okay, now it's time to stop. Right? Maybe we can also look at this quickly for the example of a higher Hurst parameter, because we have maybe some more intuition here. We have to quickly fit the model again. Maybe in the meanwhile, let me see just if this is training. In the meanwhile, oh no, sorry, I can't show you this. We have to quickly wait for the training. So this is for Hurst parameter 0.9, where we have a much more regular path, where the path for, again, for h equals to 1.0, it's just a linear line. Yep. Yep.
Thanks, Christian. So while we wait, a quick question maybe. So if the intuition for small Hurst parameter is that large spikes trigger the stopping, I'm wondering how much the results are affected by the time discretization of fractional Brownian motion.
Yeah, that's a good question. In fact, yeah, this maybe I can mention. No, I do it here. So I just want to write down the correlation function of the fractional Brownian motion. Now, if you plug in h equals to 0 into the correlation function, right, just to see what happens, and then so for h equals to 0, this will be 0. No, this will be 1 if s is equal to t. We have variance 1. It will be 1/2 everywhere else. Right. So this is in continuous time a strange process, because it's almost like some sort of a white noise with variance 1. But if you're in discrete time, and that's what your question was about, then this makes sense even if you send h to 0 on a discrete time grid. This is a well-defined Gaussian process where you have this property that you have a variance 1 everywhere and correlation to 0 everywhere. And you can actually write this as the xt j, you can write this as h equals to 0. Some standard Gaussian, the j minus an independent standard Gaussian that is, and you probably have to also scale by 1 over square root of 2. And this independent Gaussian is the same for all time points and independent of everything else. And we could actually compute using the dynamic programming principle explicitly the optimal stopping value for that process on the discrete time grid. And then you can look at that value, and if you send h to infinity, you see that this will converge to, sorry, not h to infinity. If you send the time discretization to infinity, the optimal stopping value goes to infinity. And so to your question, if you make your time grid finite, we will expect very high values for the optimal stopping value. Yep.
So for the iterated integrals, I mean, do you know what is the order of quadrature that you used, I mean, here to approximate those iterated integrals? Because this is also impacts the.
So you see that we didn't calculate the iterated integrals itself, right? We calculated the log signature with this PCH formula.
Okay.
So I don't know if you would translate this to a quadrature. I couldn't tell you now what kind of order that would be, but it's different from the approach of calculating the integrals themselves, right? Using this chain relation and this PCH formula.
Okay. So with this log, the transformation, you avoid, I mean, computing these iterated integrals.
Yeah. Yeah.
Okay. Thank you.
So here we have now calibrated the model for h equals to 0.9. So this is interesting. So at some point, so essentially what the rule needs to do is to decide, will this path go down eventually or will it go up? Right? And here you see at the beginning, maybe not clear because it's sort of horizontally moving, and it goes down, and now it's already critical. Should I stop now, or will it perhaps also switch and go up again? At the end, it goes down, and once that the rule realizes that, it will stop. Let's look at another sample. Let's see. Here did a mistake, right? This is not optimal. It thinks, okay, this goes down, I stop immediately, but in the end, it changed and it was suboptimal. But of course, you have to find the trade-off. You can't look into the future, obviously. You only have the information until each time. So you have to make a trade-off. So finally, to mention this is already pre-calculated. These are the optimal stopping values for different Hurst parameters. So this red line and the blue line are for 100 discretization points in time grid. The red line is from this Becker-Cheredito-Jensen approach. And the blue line is our signature stopping rule with n equals to, so truncation level 3. We use truncation. So as in this example that I calculated, just maybe a little bit more training, a bit more samples, and then we obtain values that are very close to these. So one would think that these values are quite optimal, but of course we don't have upper bounds, so we can't say for sure if they are optimal, but they seem to converge at some point here. So here, these horizontal lines at 0 are what I mentioned are the exact values for the optimal stopping problem with h equals to 0, and they converge to infinity if I send the time discretization to infinity. And then, as mentioned before, we can rather simply make our time grid finer and not change the number of parameters in our network, And this will, of course, lead to higher values of the optimal stopping problem. So better approximations of the continuous time stopping problems. We did this also for truncation, for time visualization 1000 and 10,000. So at 10,000, I would say that this Markovian embedding sort of could already start to have problems because there are so many, such a high number of input dimensions. So at this point, I will have here some references. I will upload this maybe to my website, so who is interested can look it up. And I will thank you for the attention.
Thank you very much, Paul, for this very nice talk. Maybe a comment at the end.
Okay.
One time was enough. You don't have to say it 10 times. Sorry? Yeah, maybe it's mine.
No.
In Zoom. Yeah.
Okay, so let's try again. Thanks again, Paul, for the talk. Maybe a comment if you can go up to the last picture, because I think this is really a kind of answer to Jiheb's question, because basically what you see is, I mean, what the difference for the different number of time steps is the quadrature error, right? In some sense, at least. So obviously, when h is very, very small, the quadrature error is actually substantial. Yes. Yes. And whereas for small for larger h, it's actually minuscule at this point. But yeah. Any other questions or comments? Or maybe somebody just want to play ball. Okay. If not, then let's thank Paul again. And we continue in half an hour with Christoph's first talk.